Hi guys, Mr. Janowski again, this time with part 5 of the chapter 9 slides. And I'm going to try to do this one quicker, although I keep saying that, and that keeps not being the case. However, I've looked at these slides. We should be able to get through these pretty quick. There won't be any Wacom tablet part to this. So let's get started. So what are the big ideas we've learned so far this year? Well, there's the most important thing you'll learn in physics all year, which is Newton's second law, F equals ma. There's also what we learned in chapter 8, which is the law of conservation of momentum. I hope that's not too annoying the way I'm asking these questions. And finally, the big idea from this chapter is the law of conservation of energy. So those are our big ideas. Everything else we've learned are smaller ideas that might fit into these, but these are the big one with everything kinds of truths we've learned. Next question, how effective is mathematics in the natural sciences? Remember the last video? I made a big deal about this. Mathematics are unreasonably effective in the natural sciences. So here's a quote from that article by Eugene Wigner. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will extend, for better or for worse, to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. So, yeah, the gist of this is the fact that mathematics works so incredibly well in the natural sciences and at explaining the universe in general, it's just really bizarre. And the more you study science and you see math pull these weird little, I don't know, tricks, the weird way the math works out and the way it applies to the universe is actually kind of bizarre. And so this whole idea, the unreasonable effectiveness of mathematics, this is part of physics, culture, science, geek, nerd culture. So if you like science, you might as well learn it now. So back to this idea of what is math. Math is truth, in my opinion. The thing that Bernard Riemann figured out about, how math works in n numbers of possibly curved dimensions, he wasn't inventing anything, in my opinion. He was discovering something. He was discovering just things that are true. Physics, on the other hand, is reality. It's really only a subset of the truth. So Einstein, when he figured out general relativity and that gravity is the curvature of four-dimensional spacetime, he only cared about four-dimensional curved spacetime because that's the only number of dimensions that describe the universe as far as he was concerned. Modern string theorists might disagree with that, but whatever. Einstein did pretty well for himself in physics. So yeah, Riemann figured out how truth and how everything works in n, meaning any number of curved dimensions. Einstein, the physicist, he only cared about four because that's what he thought described the universe. So yeah, as physicists, we look up to the mathematicians. They're always years or decades or centuries ahead of us in what they figured out for us. So what is a perpetual motion machine? Nothing is a perpetual motion machine. Such a thing cannot actually exist. What it is meant to be, it's a device that can just do work indefinitely without an energy source. It's something that you can start and it'll just keep running forever. And in some cases, some people like to think not only will the thing run forever by itself, but you can actually steal a little bit of energy from that thing and use it to power something else. It would be very nice if you could do that. People have been trying to do that for a very long time. However, it's not actually possible. So don't bother. So this guy in this Norman Rockwell, does it say Norman Rockwell somewhere? Yeah, there it is. This is a Norman Rockwell. It definitely looks like a Norman Rockwell painting. He's trying to make an overbalanced wheel type of perpetual motion machine, a very popular type to attempt to make. It ain't going to work. It never works. So the reason it doesn't work is something that we've learned in this chapter, the law of conservation of energy. So we can like to do these problems and we'll say, we're going to ignore friction. We're going to ignore air resistance. We just pretend those things don't actually exist. Turns out in any real system, if you're actually making a thing, there is going to be some kind of friction in there. And that's going to slow everything down. That's going to take energy out of your system, which means your thing is not going to run forever. Your system will always lose energy. So that's why, according to the first law of thermodynamics, you can't make a perpetual motion machine. The second law of thermodynamics also says you can't make it. Lots of different ways to say the second law of thermodynamics. One way is that entropy always goes up in any closed system. Another way is things tend towards disorder. Second law, we're not going to do that much with that this year. It's a really interesting law, though. So, yeah, if you've got extra time, take a look at that. So here's a TED video. We're not going to watch the TED video in my video. But yeah, just goes to the point, you can't actually make a perpetual motion machine. Here's another video, same exact point. This one is from Seeker. Okay, you can read. I don't know why I'm describing this to you. So here's another way of visualizing the law of conservation of energy. So I explained this back when we had class live and real and in person, but I'll explain it again real quick here. So you've got this roller coaster, starts at the top of the hill, goes down, goes through the loop, goes through the other loop, does the rest of the track. So the graphs we're looking at here, this first column represents its kinetic energy. This second one represents its potential energy. It's actually gravitational potential energy, but the GIF I found doesn't call it that. And this one, TME, is your total mechanical energy. So what's happening here is we're ignoring friction and air resistance in this case. The idea is that the energy that this card has is going to keep changing from, it starts with all potential energy and then it starts becoming kinetic. It keeps changing from one form to the other. So as one column goes down, the other one goes up by the same amount. And by so doing, they're keeping the total mechanical energy constant throughout the whole thing. So just another way of visualizing this. At every point, from the top of the track through the loops all the way to the end, energy is going from one form to the other, from potential to kinetic, and look, it's about to go back from kinetic to potential, in such a way that the total mechanical energy is always conserved. So, quick review. Just check your memory. What is the formula for kinetic energy? It is Ke equals 1/2 mv squared. So what do these terms represent? What are their units? Ke is kinetic energy. Its units are joules, because those are the units for energy. M stands for mass. Its units are kilograms. And V is velocity, and its units are meters per second. How about your formula for gravitational potential energy? That is GPE equals mgh. So what do these terms represent? GPE is gravitational potential energy. It's in joules. M is still mass in kilograms. G is the acceleration due to gravity, which is, you're going to use the positive number, 9.8 meters per second squared. You only use the negative number, really, if you're doing kinematics problems. Everything else, for the rest of the year, you'll use the positive number for G. And H is the height, measured in meters. So this is the formula people tend to struggle with the most. What is your formula for elastic potential energy? That is EPE is equal to 1/2 kx squared. So what are these terms? What are their units? So EPE, elastic potential energy, that's joules. K is what's called the spring constant. Think K for constant. The units for that are newtons per meter. And X is the extension or compression of the spring, and the units for that are going to be meters. So that's it. Yeah, hopefully this was helpful.